session, Learning to Rank for Search and Recommender System. My name is Jungshi from LinkedIn. Let's first take a look at the search and the recommender system. There are usually three stages in the system. The first stage, according to the query or user profile, documents are retrieved. This is usually done by very simple rules, and we retrieve documents um, on the order of hundreds or even thousand. The retrieved documents then uh, will be fed into a ranking system, and they will get a score, and the score will be ranked. That's the second stage. At the final stage, the retrieved document will go through another layer of ranking. So this ranking system at the last stage usually are rule-based and for different purpose. For example, the final result needs to have a diversity and a fairness. So some document may be removed and the scores may be adjusted. And this called the re-ranking stage. So let's talk about the document retrieval first. There are many ways to retrieve documents very fast. The simplest way is use a regular expression-based retrieval. So it's very similar to we retrieve records from a database. Um, Another approach is to use the inverted index. So all the documents are indexed according to the keywords, and once the keywords comes in, the relevant document will be retrieved. Recently, due to the popularity of deep learning, embedding-based retrieval are used. So the documents and the query will be mapped to embedding vectors, and the retrieval is basically looking for the nearest neighbor to the query embedding. So in this case, let's say we retrieve 3 documents. So around the query embedding, there are 3 documents are close by. That's document 1, document 2, and document 3. So these 3 will be retrieved. And 4 and 5 are too far, so they will not be retrieved. Is the scoring and the ranking. The retrieved documents together with the query will be converted to features. So we have query features and document features. All these features are fed into machine learning models. The models will generate scores for each document, and then the documents will be ranked according to scores. Different models they generate a different set of scores, and this talk is mostly about all these algorithms that inside of this machine learning models. Before we go into the algorithms, let's first talk about the metrics for evaluation. So how do we evaluate a good result, and how do we know that a result is good and a result is bad? Depending on the relevance scores, so sometimes you get a multi-level of relevance scores, sometimes you get binary scores. And for multi-level scores, there's a normalized discounted cumulative gain. So that's a NDCG. That's one of the metrics people use to evaluate the result. Then if sometimes you get the binary relevant, basically a document is relevant or not relevant, irrelevant, right? In that case, there are at least 2 metrics. One is the mean average precision, and the other is the mean reciprocal rank. So let's take a look what they are. Take a look at the normalized discounted cumulative gain, also known as NDCG. Before we go into the details of NDCG, let's look at what is DCG, the discounted cumulative gain. So it is basically weighted sum of the relevance. So here's an expression. We are given a list, and each list has a relevance score. Normally we can just add the score together, but because each document is at a different position, the position has a different weight, so we need to weight that. So the weights usually, there are different ways to define the weight, and this is one way to define it. The weight is the position plus 1 and take a log 2. Once you add this together, you get the total gain. But if you have lists of different lengths, then you get a different gain, and the gains cannot be compared because the longer the list is, the larger the gain is. So we need to normalize it to compare across lists of different lengths. So this is a NDCG, normalized DCG. The DCG part is the same. What's new here is the ideal DCG. So it's defined here. So basically, if you know the perfect permutation of this perfect arrangement of this document list, and you calculate that the DCG of that perfect list, and that's your denominator. And after this normalization, the number will be between 0 to 1, and so you can compare this number across different lengths. And the next metric is mean average precision. As I mentioned earlier, this is for the case that you have a binary scores. Let's say you just look at relevant or irrelevant, right? 0 or 1. Before we go to the mean average precision, let's first look at what is precision at k. So you look at the position at k, and you count how many relevant documents you have. And you take the sum and divide by the number of total number of document at that position until that position. Then that's your precision. So this is an example. We have 5 documents. The red ones are irrelevant and the green ones are relevant. So we can calculate the precision at the individual positions. So let's say at a 0, because this is not relevant, so we get a 0. And at 2, we have 2 documents in total, and 1 document is relevant, so we can half. And here we get 2/3. The average precision is the average over k, but only for relevant documents. This red ones, they do not count. So we do not look at position 1 and position 4. So here's how you calculate it. Precision at 2, precision at 3, and precision 4. Sorry, precision at 5. These are the 3 relevant documents, and we look at the precision. The average basically is you add them together, divide by 3, and that's the average precision. So mean average precision is another layer of average. The average is over queries. So this is the list is for single query, and we have many queries. So when we average over the queries, we get the mean average precision. A simpler metric is called mean reciprocal rank. Basically, it's 1 over the rank. Assume that in the list there's only 1 relevant document, and the relevant document position is the rank. So you take 1 over that. That's the reciprocal rank. So the better the ranking algorithm is, the higher the number is. So ideally, the relevant document should be ranked at the first. Then you get the reciprocal rank of 1. So similar to the previous metric, we take an average over the queries. Then we get the mean reciprocal rank. Take a look at the ranking models. Generally speaking, the models can be divided into 3 categories. The first category is a vector space model. So we take the co-occurrence matrix and take the vectors and we run SVD kind of operation to get the latent semantic space vectors, and these vectors we can use to look at the distance between the query. For example, look at the distance between the query and the document, and we can calculate the cosine similarity or the Euclidean distance, and these distance can be used as a metric to rank the documents. The second category is probabilistic models. One important example is the BM25. It is actually a backward model. It's based on the TF-IDF, and they calculate the score between a query and a document based on these TF-IDF numbers. Another model is the statistical language model. So you can think of the query is a text, and the document, of course, it's another text. And then you can build language models out of the document, and you look at the probability of the query given a document. And the higher the probability is, the more relevant the document is. The third category is the learning to rank models. So we see many models here. I list the three of them. There's ordinal, regression, and ranking SVM, and the lambda ranker. Well, this is the focus of this talk, and we will go into the details of individual models in the next few slides. But before we go into the algorithm, let's look at the system. So how does learning to rank system look like? So on the right side, we have a diagram. So during training, you get all these query and document lists. And this learning system will train a model, and the model will be fed into the ranking system. During test time, you get a query and a list of documents. They will be ranked, and the prediction actually is the ranked document. As you can see, that the ranking model has three components. One is the input, one is the label, and the other one is the loss function. According to the input and also the loss function, it can be divided into three different categories. One is the pointwise ranking, second is the pairwise ranking, and the last category is the listwise ranking. And we're going to go into the details in the following slides. First, let's talk about the pointwise ranking. In pointwise ranking, the loss function is based on a single query and document pair. So every time you take a look at the example, it is a query and a document pair. So there are regression-based algorithms, classification-based algorithms, and ordinal regression-based algorithms. So let's take a look at the example ranking. The inputs are the query and document feature vector pairs. Label is the relevance of the document. Loss function is, in this particular case, we are using the mean squared error. So the scoring function does is it trying to approximate the labels by minimize the mean square error. So this is a regular regression problem, right? The second category is a classification-based pointwise ranking. We have a same input, same output. Now the relevance of the document usually are the classes of the document. So if it's a binary case, you can have two classes. One is the relevant, the other one the irrelevant. So 0 or 1. And you could have like multiple classes like a perfect match, a partial match, and then maybe irrelevant. Three categories in this example. Then become a multi-class classification problem. The loss function usually for classification problem is the cross entropy loss between the label and the predicted probability. I give one example here for logistic regression. In the binary case, this is the logistic function. This is how we calculate, how to model this probability. So next category is ordinal regression-based pointwise ranking. You can think of the labels ordinals. So they have the order, right? So 0 is less than 1, less than 2. For this kind of regression, the input is the same as the pair of query and the feature and document features. Label is, as I mentioned, is probably like 0, 1, 2, 3, these kind of ordinal numbers. And the loss function, a lot of times we use negative likelihood. The output are two things. One is the weights. The other one is a set of threshold. So you can think of on a line, the thresholds basically divide this line to different segments, and your score will be in one of these segments, and the segment is the class, and you get the probability of that particular segment, and in this case we use this formula to model this probability. So sigmoid of theta minus w times the query and the document and plus some intercept. So this is a ordinal regression-based pointwise ranking. Summary. Pointwise ranking is very simple. It's only considered one document at a time. And there's many classification and regression algorithm can be used as simple as linear models, and you can use gradient boosting trees and neural networks. So lots of them. So these algorithms are very rich. The problem is pointwise ranking. You only look at the document one document time, so you ignore the other documents in the list, and that actually is a suboptimal. And also the pointwise ranking is trying to predict a score for a single document. This is not exactly what we doing in reality. In reality, we are looking at the whole list of documents and trying to rank according to relative relevance. So there's a disconnect between this particular loss function or objective function and our goal. That's why this is suboptimal. In pairwise ranking, the loss function is different. It's based on a query and a pair of documents, and so is the input. And there are many algorithms involved in this category. This is actually a very important category. I list three examples here. The one is RankNet, the ranking SVM. The other one is lambda rank. We will go over these algorithms in a later slide. The commonality of the pairwise ranking algorithm is this. So the input is a query and a pair of documents. When you put the label, we do not label the document itself. We label the pair. And if, for example, the DI and the DJ, DI ranks before DJ, we put -1, for example, and if the other way around, we put +1 as the label. So this label is different from the pointwise ranking case. The scoring function also takes a pair. So it takes a query and takes a pair of document. But in most cases, it is a function of a query and one document. And this pair can be decomposed to the difference between the document scores. That makes things easier when you build the model. So let's look at a few concrete examples. RankNet, the input is a query and the document pair. The label is +1 if the DI ranks higher than DJ and -1. So this is the same. The loss function is a cross-entropy loss. Um, we can think of the pair as they form a class. It's a minus class and plus minus one class and a plus one class, and you can predict the probability, and you use the label to form the loss function. The rank net uses a neural network as a scoring function, so it can represent a nonlinear relationships between the features and the query features and document features. So this makes this model very rich. But if you look closely, it's just a classification algorithm on the pairs. The second algorithm is a ranking SVM. So again, we have the same input as the previous case and the same label. So it's a classification problem on the pair. So here we use the SVM to do the classification. This part is the formula, and this looks very much similar to the SVM. The difference, the regular SVM, the difference is here we have the difference between the pair, the document feature, not just document itself, but the difference. That makes this a pairwise ranking SVM. Category is lambda rank and the lambda mart. These two algorithms are very similar, so I put them together. The difference here is the loss function usually is not known. So we use the evaluation matrix instead. And we also define the gradient instead of the loss function. So this is the what is different from previous two algorithms. So let's first select a metric. For example, let's use NDCG. Then we, given a list, we can compute the NDCG for the list. Then we select two documents. So that's why this is a pairwise ranking algorithm, because it always considered a pair at a time. So you take two documents, and let's say one document is more relevant to the other, and we swap the position. Then we compute the NDCG again after the swap. The data is used to compute the lambda. So the lambda is treated as the gradient to the unknown loss function. And we use the gradient to update the weights, just as we do in graded descent algorithms. Now the lambda mart uses gradient boosting tree to approximate the gradient. So that's why this is different from lambda rank. For pairwise ranking, we are considering a pair of documents at the same time. So this is closer to the actual problem we're working on, the ranking problem. That's why it achieves the better performance. But usually the complexity is higher than pointwise ranking. And looking at the pair is not still not the same as looking at the entire list. So you lose a lot. You do lose the information about just looking at the pair instead of the entire list. So the next category of algorithms look at the entire list. So the loss functions are based on the query and a list of documents. There are three examples I give here. One is AdaRank. The remaining two are very close to each other. One is called the ListNet and one the ListMLE. Let's see what they are. In listwise ranking algorithms, we try to optimize the evaluation metrics directly, for example, NDCG. But the problem with NDCG is this function is not differentiable. So you cannot take the gradient. So it's going to be hard to optimize. Instead of optimize the matrix function itself, we take a look at the exponential function of the loss. So in this example, e of pi I and y I is the loss, is the metric, and we look at the loss exponential of this metric, and we minimize this loss and we can maximize this metric. Here, pi of I is the predicted list, and you can think of it as permutation of the ground truth. Yi is the ground truth list. And then the usual AdaBoost algorithm can apply here. We can build a simple weak learner, and we find all the errors it make, and we adjust the weight of the training examples, and then we build another learner, weak learner, and accumulate iteratively. We can build a good classifier. Another category of listwise algorithm is ListNet and the ListMLE. These two are very similar to each other. So instead of work with the list of scores, they convert the scores to probabilities, and by using the Plockett-Luce model. There are different ways to compute the probabilities. One is the permutation probability. Basically, you can calculate the probability of each permutation, and it can be done by this formula here. S is the scoring function, and you get the element here, and you apply phi function here. Phi is a non-negative monotonic function. Then this is how you calculate the probability for this particular permutation. And the problem with this approach is there are many permutations. The number of permutations actually grows exponentially. So there's a lot of computation here. So a simpler one is you only calculate the top one probability. So what's the probability a document ranked at the top, right? So this is how you calculate it. So this one, it's a linear complexity. So this is manageable. The last function for ListNet is the KL divergence, or the cross entropy loss between the predicted probability and the ground truth probability. To calculate this kind of a loss function, you need to calculate all the permutations, or all the top one probabilities. So that actually causes very high complexity during the training. So one way to simplify it is, instead of calculating all these probabilities, you only look at one example and look at the likelihood. So negative log likelihood loss can simplify this computation. So that's what ListMLE uses. So to summarize, listwise ranking consider the entire list and use more information for ranking than the pointwise and the pairwise approaches. And usually it offers the best performance, but the disadvantage of this algorithm is it incurs higher complexity than the other two categories, mainly because you are looking at the entire list. So that concludes this session. Introduce a ranking framework. It's called a DeText. It combines deep learning and ranking. It supports all three ranking functions: pointwise, pairwise, and listwise. It is compatible with TF ranking, and you can easily include text features in this ranking framework. Find more information about this framework at GitHub at this link.